Okay, eerie. Well, you'll see. So, electric force on a charge. Gravity. We had a force of gravity. G(m)(m) over r squared. Falls off with as a 1 over r squared. I don't have a cool physics story for you because I don't actually know how he came up with it. But Coulomb, physicist, and I'll make one up, found that there is a similar relationship between two charged objects that there is between two massive objects. So electric charge behaves similarly to how masses interact with each other. So you have large mass creates, at least in classical physics, large masses create a gravitational force between two objects. Coulomb, and that fall off, it gets smaller as it's a 1 over r squared. As you get further away, it falls off 1 over r squared. It falls off quickly. Coulomb discovered that charged objects behave exactly the same way. He found that the force between two electrically charged objects, which I'm going to call F sub E. If that's confusing, you can call it F sub elect. Sometimes how I write it. He found it to be proportional to the two charges. So the larger those two charges, obviously the larger the force between them. It falls off with a radius squared. And he found that there was another universal constant that governed this relationship. That relationship is called K. Or sorry, that universal constant is called K. No, it's not. K is a universal constant that has a value of 9 times 10 to the 9 Newton meters squared per Coulomb squared. We don't like those units. But the units make sense, right? Like it has to have units to cancel out the 2 coulombs, and it has to have units to cancel out the meters squared. So it's got meters squared per Coulomb squared, and it leaves you with a force, so it has to have newtons as part of the units. Okay? There is and I knew the story once because I took a course on the history of physics. I knew the experiments that he did to make this happen. I don't remember them, and so I'm not going to make stuff up. The thing to remember here, though, is we do not include the positives and negatives on the charges. Crystal, can you get that? In the equation. Yep. In the equation. Oh, do not include positive or negative on the charges in the equation. The positive and negative determine direction. So we use the magnitude of the charges to give us the size of the force. And then the relationship between those two charges is going to give us the direction. Hey, John, what's up? No, let's make our own mind. It's like a bug zapper. Like you just open your mouth. Because I don't know why that whole side of the class is gone, except for Toby and Jay. Well, Toby's now gone, but whatever. Okay. Cool. So here we go. To find the direction of the force, we use the ideas from Science 10. Used to be in Science 10. Now I'm pretty sure it's in Science 9. Maybe back into middle school. Opposite charges attract. Like charges repel. Okay? So we're going to fill in the blanks to draw the direction of the charges. Like charges will attract. We said that already. Nope. I lied. They repel. Unlike charges attract each other. So then the force between these two guys is going to go which way? One's going to go up, one's going to go down. Equal and opposite. Force on these guys? In together. Equal and opposite.
Will it only be equal and opposite if equal and opposite? Or will it always be equal and opposite?
No. Forces are always equal to and opposite each other because of Newton. That's Newton. That has nothing to do with the forces. For every action, there's an equal and opposite reaction. So if this guy has a force inwards, this guy also has to have a force. If this is to the right, this one's to the left. That has nothing to do, yes, good question. That has nothing to do with the electricity and everything to do with Newton and the classical laws he laid down. I mean, lots of these things are conceptual, but they make sense. I slap you and yet my hand hurts. So your face had to have imparted something on me. So the force on which I hit you, you hit back at me. Like it's conceptually equivalent. I punch, like I fist bump you, you fist bump me. Like it has to be equal and opposite. We're gonna feel the same thing. Okay. So conceptually, he puts these things together, and that's how a lot of physics gets developed. It's like, okay, well, conceptually, and it's kind of how I've tried to teach you guys up to this point. Like, and math is the same way. Like you build on truths. Okay, we establish that this works a particular way. What are the implications behind that truth? Well, then this must be true. 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 And sometimes and this will happen to you in your education, especially those of you who go post-secondary math physics. There will be times where it becomes very, very difficult to draw a line from where you started to where you are now. And there will come a point, likely, where there will be a crisis of understanding. And what you've got to do is you've got to tie everything back to the foundation, what you know is true. Heck, this happens in so many different areas of life. If you're a religious person, this happens in that realm too. At some point, there will be a crisis of understanding from where you started to where you end. But you've just got to go back to what you know to be true at the beginning and reconnect the dots. Newton laid down for classical physics, laid down the bedrock. That has to be true for classical physics. It breaks down when things get real fast, real big, real hot, real cold. But for the vast majority of the human experience, it works. And so we go with that to be true. We just kind of carry on. The implications just kind of flow from there. And all of a sudden we're in E and M. But the dots, you can trace the dots all the way through. So let's find out what the forces are here. Let's put some values in here. I've got two electrons 1 millimeter apart. Sorry, it is a very large millimeter. Not drawn to scale. Even if this is a millimeter, those electrons are drawn way too big. Okay, the electrons are 1 millimeter apart. We know that they're going to repel each other. The question is, well, how strong is that force going to be? Well, the electric force between two charged objects is given to us using this. KQQ over R squared. 1 millimeter is how many meters? Yeah, 0.01. 001. Oh. No. 001. It's 10 to the negative 3. Milli is 10 to the negative 3. Okay. So let's plug this thing in. We know this K, this universal constant, was established experimentally. 9 times 10 to the 9. It's the easiest one to remember. Well, we've also got like 6.67 times 10 to the negative 11. There's going to be one that comes when we do magnetism. Oh. This one's the easy one, 99. 9e, like, times 10 to the 9. Q and Q, the charge on an electron is just the elementary charge. 1.6 times 10 to the negative 19. 1.6 times 10 to the negative 19 shows up there twice because there's two particles. They're both electrons. But we don't use the charges because they gave us the direction of the forces. I could have, but I'm not going to take any shortcuts when I'm first introducing something to you guys. And the distance between them is 0.001, and we're squaring that. So if you run that through your calculator, just for time's sake, I'm not going to get you to do it. I'll just tell you that it's 2.3 times 10 to the negative 22 newtons, which, interestingly enough, is going to be, bless you, the exact same force here. Because the proton and the electron have the same charge, except now that force is going to be attractive. The force here will also be 2.3 times 10 to the negative 22 newtons. That sounds like a very small force. It's not the size of the force that matters as much as, well, it also is the scale of the system. If you have a very small force acting on a very small object, that could produce a monumental acceleration. So let's analyze that. Go back to this first problem. What is it doing to the, what kind of acceleration are these guys experiencing at this point? Well, this just, again, it all comes back to Newton. F equals ma. A net force on an object is going to, a net force on an object with mass is going to produce an acceleration. So I've got 2.33 times 10 to the negative 22 is equal to, and I'm just going to analyze it on one of them. The mass of an electron is 9.11 times 10 to the negative 31. Very small object. Well, you've got 10 to the negative, ignoring the numbers out front, you've got 10 to the negative 22 divided by 10 to the negative 31. Do we remember how we deal with the division of exponents? Well, it's top minus bottom. So it's negative 22 minus negative 31. So that means we're going to add up, well, yeah, negative 22 plus 31. That's going to be times 10 to the, on the order of times 10 to the 9. That's a very large number. We're in the realm of billions of meters per second squared. So even though the force is very small, the object is even smaller. So the acceleration on that electron is going to be massive. In fact, that number is going to be this.
It's not bigger than the speed of light.
It's just an acceleration. It's not a speed, it's an acceleration. So 252 billion, no, sorry, 252,469,813 meters per second squared is actually what that number ends up being. It drops it from 10 to the 9 to 10 to the 8 because you've got a 2.33 divided by 9.11, so that's going to move the decimal place once. This is the value. The acceleration of these electrons is huge. That's the same acceleration this guy here is going to experience, because that's also an electron. The proton isn't going to feel the same acceleration. The proton is going to accelerate much slower because it's much more massive compared to an electron. Cool? Relatively straightforward, yes? Looks eerily similar. That gravity and electricity, and there's other things that are connected like this, are related to each other, has some very interesting metaphysical implications, very philosophical ideas that I'm not going to get into in this course. But stick around lunch if you want to talk about them. Very, very deeply philosophical. Now, things that are seemingly unrelated to each other have almost identical relationships is weird for most people. Here we go. So, this is a similar setup to a question I gave you for homework yesterday, except instead of dealing with the gravitational force on an object set up like this, I want to find the direction of the electrical forces on positive charge Q. You've done this. This is exactly the same. We can't find it exactly because I don't know what these distances are, but we can ballpark this thing. This guy has a charge of positive Q. That's negative 2Q, negative 2Q, and positive 2Q. So, which way, all I'm asking for is the direction of the electric forces on Q. I don't want the magnitude. I'm just going to do an analysis of the direction. Which force, or what's the direction of the force from this guy on this thing? This is negative, this is positive. It's going to have a force downwards. This guy is going to do what? This guy's going to do what? Which way? So we could find the fx component here, the fy component here, and we could analyze these guys. Looking at the shape, though, this is a rectangle, which accentuates it that much more. Which way is the direction, which way is F net probably going to end up being? Which of these forces is going to be the largest? This one. Because this is 2, this is 2, this is 2. So as far as the charge is concerned, they're all equivalent. So the part that we have to analyze to decide which one's going to be the biggest is what part? The distance between them. So the shortest distance between any of these charges is this distance here. So this force is going to be my largest, followed by which other force? What's my second biggest? Top right is going to be my second biggest. I'll call this F1, F2. So then my smallest is going to be F3. So you're going to have something that ends up looking like this. A big F1, a slightly smaller F2, and a slightly smaller, even than that, F3. So which direction, just ballparking this, should the force be on that guy there? Well, you start at where we started. And vector addition says, because that's what I'm doing here, I'm adding this vector, that force vector, and that force vector. I start at the tail of the first and I go to the tip of the last. So that is going to be my F net. So this guy is actually going to end up moving this way. Yeah, well, there's 3 vectors that are producing a 4th resultant, yeah. Flip the page. So this is relatively straightforward. I don't think I need to go through this. We kind of already talked about it. So I'm just going to jump straight down to this example down here. We want to find the force on an electron in a helium ion. So we're going to assume that we've ionized helium. Helium's a noble gas, but noble gases aren't supposed to have charge. Yeah, well, with enough energy, you can do whatever you want. Okay? You can ionize helium. Hard to do, takes a lot of energy, would be expensive to perform, but it's doable. So, ionized helium leaves you with 1 electron, 2 protons in the nucleus. And the radius of this, we're told, is 2 times 10 to the negative 11 meters. Let's analyze this. Talk to me about what's happening. Free body diagram this for me. What's going on? There's an inward force on that electron. Because he's negative, he's positive. I want to find the force on the electron. Okay, so I'm starting with, this is an electric force. It's inwards. KQQ over R squared.
Just like replacing the mass 1 and mass 2.
You betcha. It's exactly the same relationship, but dealing with the charge on the object instead. Yes, Nathan. Well, if the force is going inwards, the force is what's causing the acceleration inwards. You can't have an acceleration without a force. The force is in. Accelerations don't show up on a free body diagram. What's the charges that we're dealing with here? So I got 2 positive, 1 negative. So the charge on my nucleus is going to be 2 times the elementary charge, 1.6 times 10 to the negative 19, which is 3.2 times 10 to the negative 19. So that's my nucleus, 3.2 times 10 to the negative 19. And then I've got my electron, 1.6 times 10 to the negative 19. And we're told that the distance between them, or from center to center, is 2 times 10 to the negative 11 meters. Then we have to square that. So again, for the sake of time, I'll just run that for you. Because you can do this calculation, it's just different numbers, but it's the same stuff you've been doing for gravity. So we'll find that electric force is 1.15 times 10 to the negative 6 newtons. Which, if we look backwards, our previous force of 2.33 times 10 to the negative 22 newtons created an acceleration of 252,469,813 meters per second squared. This one is not 10 to the negative 22, it's 10 to the negative 6. substantially larger. 10 to the negative 22 is tiny. 10 to the negative 6 is much bigger. We're going the other way then. This is very big. So the acceleration on that electron is going to be massive. In the last one was big. This one's going to be, we're talking about, well, 10 to the 6 and 10 to the 22 is 10 to the 16 times larger. Yeah, kind of. That's 1 followed by 16 zeros. We're into the quintillions, at least. Okay. No, quin is 5.
Oh, well, yeah, there's quad, and then there's like.
Yeah.
Trillion.
Okay, flip the page. Let's do another one. So the force we were calculating in example 3 might seem very small. We did this already for the first one. This is the acceleration that previous example is going to produce. 1.26 times 10 to the 24 meters per second squared. Massive. Massive, massive, massive acceleration for that electron.
Wait, positive 1?
Well, it's inward, an inward acceleration. So this electron is moving incredibly quickly around, I mean, effectively, it's kind of orbiting, moving very quickly around that nucleus. Let's do this one. Example 4. We want to find the net electric force and the direction on the 1 microcoulomb charge below. There's only one positive 1 microcoulomb charge below. It's this guy that I'm going to color in green. This is the same kind of thing we could have done with gravity. There's the Earth, there's the moon. I put an object between them. I say, what is the net force of gravity? You analyze the force of gravity from the Earth. You analyze the force of gravity from the moon. You look at how they're in opposite directions. You add or subtract as necessary. The net force is going to be the one that is large. The direction of the large force is going to be the one that is large. Yes, gravity, easy. Apparently you did it last year. Apparently FGMM over R squared you did last year. A little bit. Physics 11 a little bit. And you did it again with me here. This is exactly the same. Except instead of analyzing the masses and talking about how their gravity interacts with each other, we're going to talk about how they're charged and how their electric forces are interacting with each other. So this green guy here and this blue guy here that I just colored in are going to interact in which way? Which way is the force going to go on that guy? Inwards is not an option. Leftwards. And the force, I'm going to color the other guy in pink. Which way is that force going to go? Why is it going to the right? Because this guy's negative, this guy's positive, so he's trying to attract him. He's pulling him in, it's going to the right. Not drawn to scale. So let's find out what these forces are. F equals KQQ over R squared. So that's going to be 9 times 10 to the 9. And these numbers are nice and easy. It's 1 times 10 to the negative 6 coulombs. 1 times 10 to the negative 6 coulombs over 20 centimeters is 0.2 meters. And we're going to square that. You're going to find the force here is 0.225 newtons to the left. Should be a square. We already dealt with the charges, the signs on the charges, by doing the direction of the forces. Let's do the pink one. Same deal. We already know that it's acting to the right. 9 times 10 to the 9. 1 times 10 to the negative 6. This next one's going to be 2 times 10 to the negative 6. Over, this is 10 centimeters, 0.1 squared. We're going to find the force is equal to 1.8 newtons. Right. So F net is going to be...
Would it not be negative?
No, you do not use, we do not put the charges, the sign on the charges in the equation. We've dealt with them. It's all about direction. By saying that this one's negative, this one's positive, we know it's going to the right. We're done. That's it. The sign on the charge doesn't matter.
Okay.
Sorry? Because that is the question that was defined. I want to find the electric force on that guy. Didn't read the question.
Oh, wow. I don't like being a verb.
Nobody likes being a verb. It's never a positive thing. That's not true. It's rarely a positive thing. So what is F net? We didn't pick a direction to be positive. Let's say to the right is positive because that's where my larger force is. Find F net. F net's the sum of the forces. Use the direction to determine positive or negative. So this is going to be 1.8 minus 0.225. We find a net force of 1.575 newtons to the right. Totally straightforward, yes? All we're using, we're using K, Q, and Q, not G, M, and M, but the math is exactly the same, which again is eerie depending on your worldview. Sorry? Sorry? I don't understand the question. No. No, there's lots of cool things that are going to come up yet that we haven't done yet. I am not. Ooh, there's 7 minutes left. I could do this. I'm going to show it to you. I'll assign the homework, but it won't be due tomorrow. It'll be due Monday. So yeah, you'll have time tomorrow to work on it. So I'll show you how this guy works, and then yeah, and then we'll call it a day. So again, this is a very similar question that I gave you before. When we're talking about gravitation, the example that I gave you that I'm thinking of now is I put the Earth up, I put the sun up, I put a satellite right here, and I said, okay, what's the net force on the satellite? We found the force due to gravity, Earth, satellite. We found the force due to gravity, sun to satellite. We added those forces together, found a net force. Okay? This example is exactly the same, except it's not oriented the same way. But for all intents and purposes, it's exactly the same. Because electricity and gravity are similar. Awesome. So, we want to find the electric force and the direction on the electron. This is the electron. Coloring him in blue just so it's really clear. Oh, page 359. Find this. You didn't flip enough. Okay, so let's look at what's happening here. Which way are the forces acting on the electron? Zach, that doesn't help me at all. Okay, cool. So slow down. Clearly, we have to slow down. Electrons have what charge? Negative. This one's positive. So which direction is the force from this guy? It's downwards. I'm going to draw that's pink. Let's use green. Electron has what charge? This is. So what's going to happen? The repel, so the electron's going. Yeah, Joseph, you couldn't have been more perfectly wrong. So let's figure this out. Again, easy calculation. My pink force, electric, is equal to KQQ over R squared. So that's just going to be 9 times 10 to the 9. My charge is 1 times 10 to the negative 6. Micro is 10 to the negative 6. My electron has a charge of, that's on my sheet somewhere, that's the elementary charge, 1.6 times 10 to the negative 19. The distance between them, 2 micrometers. 2 times 10 to the negative 6 squared. The hardest part of electrostatics is that the numbers are really, really small. So you got to get good at scientific notation on your calculator. That's the worst part of this stuff. You run those numbers, you'll find that the force that is in pink is equal to 0.00072 newtons. Oh, dang. Nope, did I do that right? Nope, we're good. We're good. No, I totally did that wrong. It's 0.0036. I wrote the wrong one down. If I'd let Ashton actually do the math, he would have caught me. Okay? That's the downward pink force. That's 1, that's 1.6, that's 2. Yes, okay, good. 0.00036 newtons. Sorry about that. That looks messy. Now let's do the green one. Formula is exactly the same. KQQ over R squared. That's going to equal 9 times 10 to the 9. 2 times 10 to the negative 6. Because this guy has a charge of 2 microcoulombs. Electron has a charge of 1.6 times 10 to the negative 19 coulombs. And the distance between them again is 2 micrometers. This one is 0.00072 newtons. Yep. Doesn't change my answer. I'm just copying my work from last semester. So now we want to find the net force. So what do? So how do you add vectors? Let's draw them up. So I've got one force acting this way, 0.00072, and I've got one force acting this way, half as big, 0.00036. So, did I do that right? Yeah, 3 zeros. So my net force is going to be that way. F is going to equal the square root of 0.00072 squared plus 0.00036 squared. This is because one's going right and one's going down, this is a nice, easy right angle triangle. Just using Pythagoras. We're going to find that the net force is equal to 0.00081 newtons. And in my direction, this guy here is just going to equal the tan inverse of 0.00036 over 0.00072, which is just tan inverse of a half, which is nice and easy and 26.6 degrees below left, I guess is the best way to describe which way that is. So left is that way, and it's down. It's that way.
What's that way?
The left is definitely not. Everyone can agree that Blake is wrong. He pointed up. Okay. So again, nothing about what we've just done is new. The only thing that is kind of irritating about where we're going is that the numbers get really small, which makes your math a pain to keep track of. But we've added vectors before. This is basically just the gravitation equation. And that's it. I'll tell you what the homework that I'm assigning is, but I don't expect you to do it tonight because you're reviewing for your test tonight. You'll have time to work on it tomorrow. It is this, and there's only 6 questions. 1, A, C, D, 7, 9, and 12. It's exactly 6.
I know, but A, C, D are like
Shit. That's not going to change.
Ooh, I could do some other stuff.
Oh.
4 is good.
I think it's almost 11.
That's it. We're done. It is 11:45. You guys can pack up. Thank you for letting me go all the way to the end.
I might not.
You know what? No, I'm totally going to add some questions tomorrow. That's okay.
Oh.
You know what? Maybe not. No, because 9 is harder than 8, so we'll leave 9 the way it is. Nah, 10 is fine. Because there's easier versions of like 9 is three particles interacting in a triangle. 8 is only 2 in a line or 3 in a line. So like I'm just giving you the harder one in all of these. Okay, have a great day, guys. I will see you later. I mean, unless you want to stick around, by all means, you're welcome to stay.
Philosophy.
Oh, you want to talk about philosophy?
31. I am brain dead and I.
Ooh, ask Abigail. Abigail, because she's going to benefit from teaching you. Teach number 31. 29 is B.
I don't know how.
Okay. Who wants to talk about philosophy? Is that really why you guys are sticking around?
Can I just verify